So we continue this subject as written. First of all, let me remind you that we always deal with situation when on a complex manifold, we have a holomorphic vector bundle. And we can also represent it with the following geometrical data, smooth bundle and flat d-bar connection. So I schematically write this as E is the same as a pair where E is a smooth vector bundle of the same rank, of course, and nabla bar is a flat d-bar connection. Is this 100% clear to everybody? If something is not clear, ask immediately, because otherwise you don't understand the rest. Okay. Now, last time we learned the following property of complexes of vector spaces.
Sorry, for me it's not completely clear how d-bar connection changes when you pass from one map from one chart to another.
By gauge transformation. In a local trivialization, the operator, in this case, when we trivialize the bundle locally, the sections are just vector valued functions, and the operator of d-bar connection is such a first order operator. A bar is a 0-1 form. Or better to say, matrix valued 0-1 form.
So if the transition functions are holomorphic, it changes.
No. In this setting, not. Is a matrix valued 0-1 form. Speaking about transition functions is the same as speaking about change of trivialization, because we encounter transition functions when we have overlap of two charts, and they come with two different trivializations, which are related by a transition function. That is a gauge transformation. So sufficient, for me, it would be sufficient to describe how this operator, this one, changes when I change the local trivialization. So we use changing local trivialization means we apply a matrix valued function G, which is a function defined on some in some open chart. and the function takes values in GL, K, C, and K is the rank of E, which is the same as the rank of smooth bundle. Then the operator of connection changes as follows. Oh, I better write in the other order, which means that A bar changes to G minus first, A bar G the same as usual gauge transformations, except that the differential operator is D bar.
Probably A bar.
Yes. A bar.
Thank you.
And here I mean composition of operators. G is considered here as operator of multiplication with the matrix valued function. Nabla bar is the differential operator, and again, operator of multiplication with a matrix valued function. All right. Now, as concerns the abstract complexes of vector spaces. So if we have an exact sequence of complexes, I don't remember the notation, but maybe they were like this: A dot, and then C dot 0, C dot 1, and so on, C dot n. Exact sequence of complexes means that all the errors are morphisms of complexes. Sequence. And such that, loosely speaking, the complexes C are all acyclic in the following sense, that H, Q of C, say alpha dot equals 0 for Q not equal to 0. Just to be on the safe side, let me assume that C Q, the complex itself starts from 0, equals 0 for Q less than 0, okay? Maybe the same about A. I'm not sure this is strictly necessary, but it will be safer. Then we have a sequence in cohomology, which is not exact anymore. Just a second. Oh. So we have the following sequence. H naught of C dot 0 to H naught of C dot 1, so on, H naught of C dot n. And let me denote these errors with SD, okay? So we obtain a complex formed by zeros cohomologies of the complexes C. And then the proposition is that the cohomology of the complex A dot are equal to the cohomology of the obtained complex. So I write the degree Q cohomology of the complex with operator D, and the complex itself is H naught of C dot dot. Of course, the notation could not be clear from scratch, but you should understand what I mean. It is, I mean, here I wrote it explicitly, which complex. Do you have questions concerning this? Now we shall apply this proposition. So what complexes do we have in relation with the holomorphic vector bond? So a holomorphic vector bundle gives us certain cohomology groups which we can think about as Czech cohomology for sufficiently small covering or a good covering. And the pair in nabla bar gives us d-bar cohomology, or nabla bar cohomology, which is a cohomology of the Dalbo complex with coefficients in curly E. Of the complex where the operator nabla bar maps from Q's zero Q forms. To make it clear, let me write zero Q. Zero Q on X with coefficients in the bundle. And recall that nabla bar squares to zero, therefore we do indeed have a complex. Okay, now when we have a smooth vector bundle, we also can consider Czech cohomology. So in principle, we also obtain such an object, HQ on X with coefficients in E. But let me stress that it is a smooth vector bundle. But they are satisfying the following general property, that this cohomology vanish for q greater than 0. And for q equal to 0, these are just sections of the bundle. So this guy equals space of sections for q equal to 0 and 0 otherwise. And this can be understood again as Czech cohomology for good covering. In this case, the good covering is easier to characterize for good covering. Namely, one can require that all elements of the covering and all intersections are contractible. It is sufficient to consider Czech homology with coefficients in sections of a smooth bundle.
And why this happens? This happens because there is too many smooth functions on manifold.
Yes, because of this, yeah. The main property which helps to prove this is that any section can be continued from a closed subset to the whole X, as I mentioned above. This is the main. No, if you want to make contact with terminology, E, what is called is a fine, flabby sheaf. Does not matter what it means, which is the same as any section given on a closed subset in X can be continued to X. And this property, again, it's a general machinery. This property can be seen as a consequence of the fact that E is a fine sheaf. It's just terminology. These words are just terms. Fine sheaf, which means that E possesses what is called partition of unity. And partition of unity is, you probably know this from geometry, when you have a set of functions which each of them is defined on some small set, and they everywhere sum to 1. And this is a similar property, but you use not functions, but endomorphisms of it. I'm not going to describe this in detail, just if somebody will look in textbooks, just for your orientation. So I put this in brackets as a comment. All right, now let us consider the following situation. Without explanations, I will call it Dalbo resolvent of a holomorphic bundle E. This is the following sequence. Let me write it as follows. First, we start from E, then we write smooth vector bundle corresponding to our holomorphic bundle. And next we write 0-1 forms with coefficients in E. Let me write it as, I don't have notation for this. Anyway, I have, no, okay, I write it as this. A01 tensor with E, so on. A0n tensor with E. And the tensor product is taken over smooth functions. Because this is what I write in here is just the tensor product of smooth bundles. A0Q is a bundle, vector bundle, a smooth vector bundle of 0Q forms. So all the participants except the Roman E, this guy, are smooth vector bundles. And the first term is a holomorphic bundle. And what are the errors? The errors we understand in the following sense. This means, if you want, it means symbolically or literally, the main thing we shall mention in a second means inclusion or embedding of local sections of E, which are holomorphic sections, because we speak about the holomorphic bundle. As a subspace of local sections of a smooth bundle. Which are C-infinity sections. And the errors like A0Q tensor E to, I write here nabla bar, is a differential operator on smooth sections or on smooth forms with coefficients in bundle E. And local sections. When I say local sections, I mean local sections for arbitrary open subsets. Simply collection of all possibilities. Now, what does it give me? It gives me this sequence, which is a little bit vaguely described what it means. But this sequence clearly gives me the corresponding sequence of Czech complexes. So the sequence star produces the corresponding sequence of Czech complexes. I shall not write it because it's just a repetition of the sequence star, replacing each term with the corresponding Czech complex. note again that the sequence star is not a sequence in the category of smooth bundles or holomorphic bundles, because the errors are not morphisms of bundles. In particular, all but one are differential operators, right? Since it is a linear map on local sections, therefore it gives us some maps between Czech complexes which consist of local sections. Now, if the covering, which is supposed in the notion of a Czech complex, if the covering is small enough, each participant of the covering, each intersection, and so on, if the covering is small, the sequence of Czech complexes is exact. Why? Because we have Dalbo lemma. The sequence is exact. This happens due to Dalbo lemma. Let me remind you that Dalbo lemma is like Poincaré lemma, is a local statement that any d-bar closed 0-1 form or 0q form is exact, which exactly means or precisely means that all these errors form an exact sequence. And exactness in this term is simply because holomorphic sections are subspace in smooth sections. So this is an embedding of spaces, of vector spaces. And exactness in this term is because holomorphic sections are the kernel of the d-bar operator. Let me write the letter thing here. In particular, holomorphic sections of our holomorphic bundle on any open subset, not necessarily, in this case, not necessarily small, is the kernel of Dalbo operator acting from sections, okay. From sections of smooth sections of E to 0-1 forms. Okay. Now, since all the participants on the right, I mean, all the participants here are smooth vector bundles, the Czech cohomology vanish for q greater than 0. And we obtain the situation described the situation of this complex, of this sequence of complexes, which brings us to this proposition. Let me say that they are acyclic in the above sense. Uh, uh, so from the sequence of in Czech complexes, we obtain a sequence of global sections, which is zeros cohomology of the bundle. We get this a complex of H naught X A 0Q consisting of these guys, which is the same as global sections. This, in our other notation, this is the same as 0Q X E. Okay, is it clear? Which looks, and the sequence looks as follows. But now we deal with global sections, globally defined 0Q forms. And according to the abstract setting here, we obtain the proposition that the cohomology with coefficient in holomorphic sections is the same as cohomology of the global Dalbo complex. The right-hand side is cohomology of the complex of global forms. A remark without explanations is the following, that one can give very parallel proof of the de Rham theorem, which you can find in textbooks easily, or ask me separately, because I don't want to spend time on this, but nevertheless, it's probably useful to mention. So the de Rham theorem can be proved in a similar way. Another thing which should be mentioned probably, an exercise is the following, that exercise. I have already given the proof of the algebraic statement about this statement as an exercise. So I repeat this. But I also appeal to you to think, to compare this abstract consideration abstract in quotation mark proof with the following. I already explain the most direct way of proving such statement in the following way. Say if say omega, suppose it is a 0-1 form on X with coefficients in the smooth bundle, which is nabla bar closed. So it defines a certain cohomology class. And we want to obtain it as a class in cohomology of no, say Czech cohomology of the holomorphic bundle. How do we do this? We first omega restricted to a small covering, to an element of a small covering, is exact. Not alpha is bad. Let's say eta alpha. And now I repeat what I already said some days ago. And now eta alpha minus eta beta is holomorphic. On the double intersection, and defines a Czech Banka cycle. Now, if you write everything, think for not only for first degree, but for arbitrary, and write everything in an accurate way, we obtain the Dalbo theorem, which we proved reducing it to some more general proposition. Okay, but thinking about the relation of two ways of reasoning is useful.
But isn't this cycle in an image of differential, by definition of differential in Czech complex?
If it would be in the image, it would be trivial in cohomology. In general, not.
But by definition of first differential in Czech cohomology, it puts like local something defined local.
Yeah. Look at here. It is written as a difference, like Czech differential of something, right? But these guys are not holomorphic. They are smooth.
I see.
Is, in a sense, it is you represent a non-trivial Czech cycle for holomorphic sections as a trivial one for smooth ones.
I see. Thank you.
Mm-hmm. And this is, in a sense, a key thing which proves this proposition. Because here we use acyclic complexes, but these complexes are acyclic. All Czech cohomology, all cohomology except degree 0 vanish. And this is analogous. This plays the same role as here. Here, what if I go from the other side, given maybe non-trivial Vanka cycle, representing, I read it in Czech cohomology of holomorphic sections. Say phi alpha beta. Let me mention that it's a Czech cycle. Phi alpha beta. So what is phi alpha beta? It's these are holomorphic sections on double intersections, right? Satisfying one cycle property. One can always find smooth sections. This is a construction in the opposite direction with respect to this one. One can always find a smooth. One can resolve it in the smooth setting. Smooth sections. Eta alpha. So these are sections over U alpha of the smooth bundle, okay? Such that phi alpha beta is eta alpha minus eta beta. And from these smooth sections, you can now obtain a 0-1 form if you reverse the construction. Okay, I stop here, but this is a good point for everybody to think. All right. So let me just write this. We have proved cohomology of a holomorphic bundle is the same as Dalbo cohomology with coefficients in E. Okay. Now, just
Probably if you want to make a break, it's a good point to make.
Absolutely. Thank you. I forgot. Okay, and we work until 4:10 after that. So we meet at 3:25. Okay. Let us continue. Now, let us call the next topic, which will be the number, I guess, 1.5. Let us call it Cleomorphic line bundles. So this will be a particular case of the general subject on holomorphic vector bundles, that is bundles of rank 1. So X, as always, a complex manifold. And now I will use the letter L. Rank 1 holomorphic vector bundle, which is the same as saying line bundle. Now the transition functions of a line bundle take values in matrices, so to say, matrices 1 cross 1. So these are phi alpha beta. Simply, I can say, do I have a notation for this or not? Let me write simply as this. So they take values in in complex numbers without 0 and are holomorphic. Which satisfy the one-car cycle property. The dots means point-wise multiplication of functions, of course. Now, as someday we already discussed that it is tempting to pass to logarithm and write it in the additive way, but then we can meet, how to say, then the logarithm does not have to necessarily satisfy, give 0 at the right hand side. The sum of logarithms may differ by 2pi integral number. And this is reflected in the following. First of all, this data can be understood, what is written can be understood as a one-car cycle in Czech cohomology for multiplicative abelian group. Czech one-car cycle with coefficients coefficients in okay, non-vanishing holomorphic functions. Let us introduce such notations. Let curly O be the trivial and trivialized holomorphic bundle whose sections are arbitrary holomorphic functions. Be trivial, actually trivialized, because we have a distinguished section equal to 1. Trivialized. Homomorphic bundle. In terms of sheaves, it's a sheaf of holomorphic functions. Holomorphic bundle whose sections are holomorphic functions. Now let O star be the same thing if we require that the functions do not vanish. So it is not a vector bundle. If you want, it is a principal bundle, but again, it is a trivial one. I simply write B a bundle. This is because I'm not allowed to use the word sheaf, not to waste your time explaining what sheaf means. B a bundle whose sections, by sections I mean local sections, on arbitrary subsets, whose sections are non-vanishing. Holomorphic functions. And now the most funniest thing will be let Z denote a bundle, but now in quotation marks. Actually, you should replace it by the word sheaf, whose sections are constant. Constants belonging to integer numbers. I short for brevity I write it in some tautological way. What I mean, why do I need here? Do I need this? We have an exact sequence. Here, the second error is the exponential map. Exponentiating a function, we obtain a function which nowhere vanishes. And the kernel is that. The constants equal to integral numbers or proportional. If you want, here is 2pi. Now, in what sense we have such an exact sequence? If we consider local sections on small sets, then the sequence is exact. Okay, on the whole of X, it may happen that we don't have sections of this bundle, for example, at all. But on small sense, we always have plenty of holomorphic functions, vanishing or non-vanishing, also constants, everything. Now, this, again, this a little bit vague description produces a sequence of Čech complexes. Again, for a good covering, or small enough. What are these Čech complexes? Z defines as a Čech complex with where, okay, let me just write explicitly. It produces the following Čech complex: C Q of Z. By definition, it is a direct sum over all. Okay. It's over all q-tuples of indices such that the corresponding intersection is not empty. And we require that all intersections are connected. It is always like this. When we work with Čech complexes, it is convenient to assume that all the elements of the covering at all the intersections are connected. Otherwise, here I will write Z. So it's the direct sum of copies of Z in the amount equal to, in the number equal to the number of q-tuple intersections. But if an intersection would consist of two components, for example, I would have to write two Z's for it. Therefore, I assume that all are connected, okay? And the bundle O produces the Čech complex, which is a direct sum over the same set of holomorphic sections, holomorphic functions over U. And O star produces the same thing for non-vanishing functions. And now, this short exact sequence star, as I already written, gives exact sequence of the shape C dot Z, C check dot O, C check dot O star. And therefore, long exact sequence in cohomology. Now let us write this sequence. The Czech cohomology of the first complex is simply Petty cohomology with integral coefficients. So we get H naught X Z. This is topological Betty cohomology, nothing else. Now, as we know, the cohomology of this guy by Talbot theorem, it's the same as zero Q cohomology. But at first step, it is just H naught C dot, X O, which are global holomorphic functions. H naught X O star. Then we continue to the first cohomology. I leave the space here for a moment. So we have H1 XZ, H1 XO, H1 XO star. And then we have H2 sorry, I left too much. H1 XO star. And now H2 XZ. And then something else. First, let us look at the 0 degree cohomology. And suppose that X is compact manifold. I haven't written this. Okay, I add here compact, all right? In this case, the global holomorphic functions are just constants. So this is a copy of C. And I remind ourselves that this is because X is compact. By the same way, in the same way, this guy is C star, non-vanishing constant functions. And this guy, in any case, is Z. So the sequence 0, Z, C star, where here is the exponential map, here is multiplication with 2pi, is exact by itself. So actually this error is 0. Okay, is it clear? Therefore, here we obtain a sequence we start from 0 and then H1 and so on. All right, so let us look at this sequence now. This is the main subject of our focus now. So what do we have here? H1 of XO by the previous subsection is nothing but H01 of X, right? Now, H1 of XO star is can be called the moduli space of line bundles over X. Because the elements of this cohomology group are transition functions of a line bundle, right? As we started with this in, it's from here. And transition functions are defined up to holomorphic gauge transformations over intersection, over open elements of the covering. And this is exactly the Czech co-boundaries. Do you have questions concerning what I said? This word moduli space, of course, does not mean simply the set of isomorphism classes. When we say a moduli space, we mean that it has to be some complex space, or better, a smooth complex manifold. But in the case of line bundles, this is exactly happens. We shall, of course, many of you know this already, but we shall see this a little bit later. It's actually always a complex torus. And in the case of line bundles, the moduli space has a separate name. It is called the Picard group of X.
So probably I missed, this is moduli space because all the higher terms are vanishing.
Higher terms of what?
I mean, in this long exact sequence.
No, it's a separate consideration. What are elements? Of this cohomology group? It's a class of Czech Wanka cycles, right? By definition of Czech cohomology, but now it's the only difference, we write the abelian group in the multiplicative notation. That's all. Okay. And to Czech, the parentheses mean that I consider the set of such holomorphic functions phi alpha beta for all pairs alpha beta, for all double intersections. And the two Czech cycles are homological, cohomological, logical, if they are related by holomorphic gauge transformations. All right. And this is the set of such equivalence classes of Czech cycles is by definition the first Czech cohomology. But now this cohomology group enters into a sequence which will be useful for us, okay? Now, the map from H1 O star to H2 is nothing but the first Chern class. Let me write this exercise as with the words, not proof, but let me write it less strictly. Convince yourself. You can do this on examples, for example. For instance, this map is the first Chern class. I mean that for an element of the Picard group, which is a set of isomorphism classes of line bundles, holomorphic line bundles, we take some class of a line bundle and map it to the first Chern class of L in H2. Okay? Now, consider the kernel of this map. Now, first of all, the Picard group is always the sum over the values of the Chern class, all possible values. Let me say like this, say gamma, where gamma runs over the image of C, over all allowed first Chern classes of line bundles, of holomorphic line bundles, of image of C1 in H2 with integral coefficients. So the component is just the set of holomorphic line bundles with a fixed Chern class. Set of isomorphism classes. Please ask any questions because there is now nothing complicated in what I'm saying. But if you are not acquainted to notations, maybe the questions can arise. So ask immediately. In many cases, like projective spaces, for instance, for projective spaces, the CPN the cohomology, the second cohomology is simply Z. Therefore, okay, and H1X O is simply, which is, I remind you, the Dalbok homology of type 0, 1 is 0 projective spaces, right? Because, for example, because they are Kähler and simply connected. Therefore, the Picard group of a projective space is simply the sum of the sum runs over integers and each for each k this guy is consists of 1 point, so it's simply the same as that. On projective space, holomorphic line bundle is completely characterized by its first Chern class. How do we see this from the above picture? Look at here. Let me temporarily use some other color. For a projective space, this guy is Z, this is 0, therefore this guy is Z, right? The next guy is also 0, as you can check. I should have written here, okay. The guy after the H2 with integral coefficients would be H2 of XO, which is also 0 because it's the same as 0, 2 homology, Dalbok homology. Was it clear what I said now? I should repeat. But in general,
you prove now that peak CPN is Z, yes?
Yeah.
And how? What is the order of arguments?
Again, we have a long exact sequence. All right. This one. The cohomology group H1, this one, is 0. This group is Z. And the next one, which I did not write, but which is H2XO, sits here, the next term, is also 0. Therefore, we obtain such a situation 0 H1X O star H2 XZ 0. Our exact sequence reduces to this short two terms, and this means that the two members are isomorphic. If such a sequence is exact, what does it mean? That this map, its kernel equals to 0, so it's an embedding. Its co-kernel also is 0, so it's surjective. This is an isomorphism.
Yeah, okay.
But in general, all the members can be non-zero. So an exercise is should be the following. You should realize what is the image over. First, look again at the portion of the exact sequence which is H1 X O star, which is the Picard group, maps to by first Chern class maps to H2X Z. And now I write it in this form, H02 of X. And now the allowed Chern classes is the image of this map in H2. So not arbitrary elements of the second cohomology group can be a Chern class of a line bundle, of a holomorphic line bundle. The word holomorphic is crucial here. Only those who belong to the image. And the image is the same as the kernel of the next map. Let me say F. So the allowed Chern classes of holomorphic line bundles belong to the kernel of F. Describe it. What is this kernel? And then you will understand what are the allowed Chern classes. But probably somebody of you can give an immediate answer without proof, just on geometrical understanding. What distinguishes Chern classes of holomorphic bundles from Chern classes of arbitrary bundles? What is the main property?
Probably they belong to PP forms.
Exactly. Exactly.
But why?
The easiest way to prove, doing this exercise, you will prove this statement for line bundles. For vector bundles, it's not that easy. But if we consider Chern classes in terms of connection and invariant polynomials of the curvature, then I will write now as a reminder for a holomorphic bundle, not necessarily a line bundle actually, L. Any holomorphic vector bundle possesses a connection I mean not D-bar connection, but just ordinary connection, whose curvature say F is now in quotation mark is 1-1 form. In quotation marks because curvature is not a true form, right? But I guess you understand what is meant here, and therefore, say the trace of F to the power P is a P comma P form. In particular, the first Chern class is a 1-1 form, is represented by a 1-1 form, okay? But now you should see this from looking at the exact sequence. Okay, now let us look at the another portion of the sequence. Zero, H1 with integral coefficients, just the beginning, the first non-trivial part of the exact sequence. H1 XO. Now the Picard group. And now let us denote this by this guy. I'm thinking which letter to use for this. In principle, in many cases, we could write this in this way, but in general, it's very difficult to give sense to this, to give sufficient sense to this notation. But therefore, again, this is in quotation marks. But now let us denote this simply by C, okay? And for let peak 0 denote the kernel of C1. That is holomorphic line bundles with which are topologically trivial, actually. When I say a holomorphic bundle which is topologically trivial, is it clear for the audience? Then we have a shorter sequence. Okay. Now from this we should prove, or simply observe, maybe better to say, that peak 0 is a complex torus. You simply should decode what is written here. It's, I mean, it's a check for your understanding of what is written here. It's not really a proof. It's already written. Okay, and this should be the first part. The second part should be the following. Show that peak gamma of X is the same as peak 0, but not as a group. Peak gamma is not a subgroup. Peak 0 is a subgroup in the peak. I did not say why it is a group. Okay, I guess you know, but nevertheless, as a complex manifold. For any gamma belonging to C, not to C. How did I? To C, yes, to C. C is a set of allowed Chern classes. And the last thing to finish very fast, I'm saying very. Again, recall of X is an abelian group with respect to a tensor product of line pandas. This, I guess, you should know. But again, if this last remark will produce problems, immediately ask me at some moment. Okay. Now time is over. Questions, please. No questions. Okay. Then, thank you very much.